Okay, next is heap sort. So the properties of a heap. Heap is a tree structure used in the heap sort algorithm. Actually, it is a tree structure. Suppose H is a complete binary tree with n elements. So this heap H is a complete binary tree with n elements. So suppose H is a complete binary tree with n elements. H is called a heap or max heap if each node n of H has the following property. This property is very important. Actually, we are having two types of heap, max heap and min heap. If it is a max heap, or simply it is known as heap. If it is a heap, then it is known as a max heap. So it will be a complete binary tree with the following property. So first is value at any node must be greater than or equal to value at each of the children of n. So this value of each node must be greater than or equal to the value of at each of the children of n. So it must be greater than or equal to the value of children. The value at n is greater than or equal to value at any of the descendants of n. First of all, it must be greater than or equal to value of any children. At the same time, this value must be greater than or equal to any of the descendants of n. H is called a min heap. So this is the property of max heap. Max heap means the value will be greater than or equal to. Then what about the min heap? Min heap. But in the case of min heap, the value will be less than or equal to the value at any of the children. Okay, one example. So this is a heap data structure. Heap is a nearly complete binary tree with the following properties. Structural properties. All levels are full except possibly the last one, which is filled from left to right. A heap is a nearly complete binary tree. Means, so this is a heap. This is an example for a heap. Means the structural property means all the levels are full except possibly the last one, which is filled from left to right. Look at this level. This level is full. Only one element is present at the root. This element is the root element. We cannot have more than one element at the root. Next level. Next level means this 7 and 4. This is the level 1. Is it okay now? Okay, we are having, so this is level 0.
Point heap data structure slide matram.
A heap is a nearly complete binary tree with the following two properties. Structural property, all levels are full except possibly the last one, which is filled from left to right. So this one is level 0 and this one is level 1. Level 1 means, so we are having two elements at level 1, that is 7 and 4. How many children are present for 7? How many children are there?
2.
2. So for node 4,
No children.
no children. That means the first nodes from left to right, all the nodes will be filled. So here 7 is filled completely. 7 is full. All levels are full. So in this case, this means this is level 1. This is level 1. Okay, 7 and 4 means these elements are included in level 1. So this 7 has 2 children, means all its level are filled. What is the maximum number of children? Since it is a binary tree, what is the maximum number of child possible? A heap is a nearly complete binary tree with the following two properties. First property is structural properties. That means all levels are full. All levels are full except possibly the last one, which is filled from left to right. Here in the first level we are having a single element 8, and in the next level we are having two elements 7 and 4. In level 1 we are having two elements 7 and 4. Again for this 7 we are having two child 5 and 2. But there is no child for 4. 7 is completely filled with two children left and right. So this is vacant. We cannot add this 2 as right or left child of 4. The next property is order property or heap property. For any node x, its parent node must be greater than the value of the parent node must be greater than x. So in this type of heap, the root is having maximum element of the heap. So here maximum element possible in this tree is 8. So 8 is at the root element. So always in max heap, the maximum element will be at the root. A heap is a binary tree that is filled in order. Then array representation of heap is stored as an array A. So here this is our heap and root is stored at element 1. This here the root is 16. So 16 is stored at A of 1, first position. So this root is stored at the first position, A of 1. Root of the tree is at A of 1. So this is 16. Then next. So what about the left child? So we had already studied that this left child is stored at 2i position. So this is A1. Parent is stored at A1. Means the child will be, left child will be stored at 2 into 1. That is second position. So the left child 14 is stored at second position. Then what about the right child? Right child will be stored at 2i plus 1. That is A1 child. 16 is stored at first position. 16 is stored at the first position, that is A of 1, and the left child will be stored at 14, that is A1 into 2. That is left child is stored at 2i, 2ith position. So I means value of I is 1. So 2i means 2 into 1. That is at second position we will store the left child. And right child is stored at 2i plus 1. 2i plus 1 means value of I is 1. So 2 into 1 plus 1. That is 3. So right child will be stored at third level, third position. So actually we will write level 0 element first, that is 16. After that we will write the level 1 element. Level 1 element means 14, 10. After that we will complete all the level 2 elements. Which are the level 2 elements? Tell me. 8,
7, 9, 3.
7, 9, 3. So after this 10, we will store 8, 7, 9, 3. After that, we will complete the next level 2, 4, 1. 2, 4, 1. So first, actually the condition is like this. First parent node will be stored at ith position, and its left child will be stored at 2ith position and right child will be stored at 2i plus 1. That is the logic. Same as the tree representation. So parent of ai is stored at floor of a of floor of I by 2. Heap size of A must be less than or equal to length of A. The elements in the subarray A of n by 2 plus 1 to n are leaves. Tell
Node
me what?
which do not have child nodes.
Yes. Nodes that do not have child nodes are known as leaf nodes. Which are the leaf nodes here?
2,
2,
4,
4,
1,
1.
and 2, 9, 3.
2, 4, 1, 9, 3. So 5 leaf nodes are there. So the elements in the subarray A of n by 2. What is the value of n here? N is 10. N means total number of elements. Elements are there. So 10 by 2. 10 by 2. What is the value of 10 by 2?
5.
5. So 5 plus 1 elements to n. So maximum there will be 6 to 10 elements will be leaf nodes. Okay. So here we are having 2, 4, 1, 9, 3 are leaf elements. Okay, can you view the slides? Okay, how to represent the heap? So here we are using a array to represent the heap. So the first level, this first level 90 is stored in index 1 and the next level elements, that is 60 and 52. This 60 and 52 are stored in the next indices. That is, first in the first index we will store 90 and the left child is stored at second index and right child is stored at third index. That is, left child is stored at 2i location and right child is stored at 2i plus 1 location. Then we will store after 90, we will store the left child of 60. That is, left child of 60 is 27. It is followed by the right child of 60. That is 36. Then we will store the child of 52. Left child of 52 is 47 and right child of 52 is 35. Like that we will continue. So this heap is maintained in memory by a linear array. So indices are also actually this one is 7. 35 is stored at 7th location. And at the 8th location we will store this 10, then 9, 17, 10. At the 10th location we will store 20, then 30, then 10. Like that we will store the heap. So in the previous class also we had discussed about max heap and min heap. In the max heap, we will store the largest element in the root. So check at this example. Actually, the largest number in this series is 24. So 24 is stored at the root. So 24 is the largest number. So this is the max heap. Look at this example. Max heap means the largest element is stored at the root. So in the min heap, here we are storing the smallest element in the root. Look at this example. Here the largest element is 24 and the 24 is stored at the root. And look at this example. Here the smallest element is 4 and 4 is stored at the root. So this is an example for a min heap and this one is an example for a max heap. Here we are concentrating on max heap only. So heap sort steps. First of all, we have to build a heap with the given set of data. After that, we have to delete the root node from the heap. Then rebuild the heap after deletion. Then after that, place the deleted node in the output. Then continue step 2 until heap tree is empty. So first step is to build a heap. In the previous class, we had
Slide.
studied how to build. Slide not visible.
ഇല്ല. ആ. ഇപ്പൊ വന്നു.
Okay, these are the steps of heap sort. First, we have to build the heap. Then we have to delete the root node from the heap. So first we have a heap. Then we will delete the root node. After deleting the root node, we have to rebuild the heap or adjust the heap. After adjusting the heap, next aim is to place the deleted node in the output. That is, we are deleting the root node and we have to place this deleted node in the output. Then we have to continue this step until heap is empty. So first delete the root node, then rebuild. Again, deleted node is written in the output. So look at this example. Numbers are 7, 4, 3, 1, 2. So first our aim is to create a heap from these elements. So first this 7 is the root node. Then next element is 4. Can you view it? I am drawing the tree. Can you view it?
കാണാം.
Okay, tell me the numbers. 7,
4, 3, 1, 2.
7, 4, 3, 1, 2. Okay. First we have to, for performing heap sort, first step is build a heap. So we are going to perform this step. Build a heap. So 7 is the first element, so it will become the root. Then next element is 4. Where we have to place this 4?
Left of 7.
Left of 7. Then what about the next element? 3.
Right of 7.
3.
Right.
Of 7. Because the child, the only for a heap, we have only one property. The value of the parent node must be greater than its children. Value must be greater than the children. So this is 3 actually. Okay. So after that we are having 1. 1 is at. So
Left
actually
of
the nodes are placed from left to right. So here this level 0. Here maximum possible node is 1. At 0th level, maximum possible, this is level 0. This one, level 0, maximum number possible is 1 only. This is level 1. Maximum possible is, how many numbers are maximum possible? 2, because it is a binary tree. Okay, if it is a ternary tree, how many nodes are possible in level 1? Ternary. What about ternary? Ternary means how many children are possible in ternary?
3.
Ternary, yes, 3 children. Ternary means 3. So we are having 3 children for each and every nodes. So okay. So level 1 is over. Actually in level 1, we are having 2 child. So we cannot add more child to this level 1. So we will move to the next level. Next level means we have to add the child, the node at the leftmost position. Here leftmost child is 4. We have to place this 1 as the leftmost child of 4. Okay. What is the next element? Next element is 2. So what is the position? After this, we are processing from this left to right. Left to right. Processing from, hello?
Hello? കേൾക്കാം മിസ്.
Hello.
Hello?
Okay, okay. So we are okay, okay, okay. We are processing from left to right. So we had placed this 1. Next element is 2. So we have to place like this, right child of 4. So all the elements are placed. So we will get a tree. Next step, actually, the heap sort. First we have to what are the steps in heap sort? First we have to build a heap. Build a heap is the first step. So next step is we have to delete the root node from the heap. So now we had completed the first step. Building a heap is okay. Now delete root node from the heap. After deleting the root node, rebuild the heap after deletion. So this is our next step. After rebuilding, we have to place this deleted node in the output. So we have to perform the second step. So we are having 5 elements, 7, 4, 3, 1, 2. Next aim is to delete the root node. Which is the root element? Tell me. Root element here.
7.
7. Yes. Yes, 7. So we have to delete this 7. Is it okay? Slides are okay now. We have to delete the root element. Which is the root element? 7. So this 7 must be deleted. So 7 is deleted means we have a vacant space at this location. I think you can't view. So first step is building the heap. Building the heap is over. Now we are going to delete the root node. So after deleting the root node, we have to rebuild the heap. So we are going to rebuild the heap after deletion. So first case, we are going to delete this root element. This is our root element. 7 is our root element. 7 is our root element. So we are going to delete the root element. Delete the root element means this one is deleted. 7 is deleted means there will be one hole. There will be one vacant space at the top. So the remaining thing will be like this. So now next step is to rebuild the heap. Rebuild the heap means move this some element to the root. Actually, what are the child of that? Which elements are the child of this root node? Actually, root position is vacant. We have to check the child of root position. Which elements are the childs?
4 and 3.
Yeah, okay. So which element is moved to the root?
Greater 4.
Yes, since we are considering the max heap, we have to move the maximum element from the child. So 4 and 3, maximum element is 4. So we are going to move 4 to the root. So the root becomes 4. Again, this position becomes vacant. This position is vacant. So which element is moved to this position? Okay. Then we have the heap. This is our heap. This is our heap. So now next step is to delete the root element. Deleting the root element means the root element is 7. So deleting the root element. So this position will be vacant. So after that we are having 4, 3, 1, 2. So this position is vacant. So what we are going to do is from the child, this 4 and 3 are the child. Among the child, 4 is greatest. 4 is the largest number. So we are moving 4 to this location. Again, this position is vacant. This position is vacant means we have to move the maximum element from the child. Which is the maximum element?
2.
This is the whole. Yes, 2 is the maximum. So we are moving to this location. Okay. And actually, we are removing 2 from this one. And you have to exchange the root element with this 2. Actually, 2 is the last element in the series, right? Am I right? 2 is the last element in the series. Just to represent this as an array. That means representing this as an array means 7. It is followed by 4. It is followed by 3. It is followed by 1. And it is followed by 2. This is the array representation of this tree. So actually what we are going to do is we are exchanging this element with this vacant position. Actually now after deleting this one, this location will be 4 and this location is having 3 and here we are having 2 and this position we are having 2. Okay, after that there is one vacant position. So we are moving this 7 to this vacant position. So our idea will be like this. So that means we can move this 7 to this location. This 2 is the last location. So we are moving this 7. After deleting this 7, we had moved this 7 to this location. Actually, this is already deleted. No need to consider it further for building the heap. We are just placing the 7 at the last position. That's all. Then only we will get the sorted list in the corrected array. I will explain it. Okay. Now we have to delete. What is the next step? Can you tell me the next step? Hello, can you tell me the next step?
4 അടുത്ത റൂട്ടിന് place.
Yes. Next root element must be deleted. This is the root element. So we have to delete the next root element. So 4 is deleted. So again, one vacant position is created. So one vacant position is created at this location. So which element is moved to this location?
3.
We are having 2 and 3 as child. So maximum element is 3. So move 3 to this location. And 2 will remain here. Okay. Hello.
കേൾക്കാം.
Okay. Okay. Then again, 3 is moved to that location and you will have 1 and 7 is placed at this location. Okay. So after this one, we are having 3 at this location, then followed by 2, and the elements are 1. So that's all. Then after that, we are having 7 at this location, and we have to move 4 to this location, right?
Huh.
Is it okay? Because actually, I will explain with this array. Initially, we are having array like this. 7 is there. Can you read the elements? Initial array.
7, 4, 3, 1, 2.
Hello. Initial
Hello.
heap. Hello.
7,
7, 4.
4,
7, 4,
3, 3, 1, 2.
4, 3, 3, 1, 2. So our first step is to exchange the first element with the last element. Means you will get like this. You can do like this also. 1, and we had exchanged this one. So 2 will be at this location. You can do like this also for building the heap. I think this method is more efficient. So root element is 7. After that, it is followed by 7 means after that it is followed by left child. Left child is 4 and right child is 3. After that, which is a left child of 4? 4 left child of 4 is 1 and right child of 4 is 2. So you will get an array like this. Is it okay? Any doubts?
Illa.
Hello. Okay, now it is clear. Okay, so the next step is you can build a heap like this also. We have to exchange this 7 with the last element. The last element is actually 2. We are going to exchange these two elements. These two elements means the after that you will get a heap like this. After that, we just exchange these two elements. Okay. Now our root contain 2, 4, 3, 1, 7. Actually, 7 is deleted element. You can put a cross since it is deleted. Now again you have to rebuild the heap. Actually 2 is at the root. You have to compare it with the children. What is the value of left child of the root?
4. 4.
4. Right child?
3.
Right child?
3.
3. So how to readjust this heap?
X 4 to exchange.
Yes, 4 2 exchange. Exchange 4 and 2. Since 2 is less than 4 and 3, we have to do one exchange. Maximum element is 4. So we can exchange 4, 2, 3, 1, 7. This is left child. This one is right child. This is left. This is right. Actually, 7 is included already. So our new heap will be like this. You can represent the array also. Now 4, 2, 1, sorry, 4, 2, 3, 1 and 7. 7 is already added. Okay, what is the next step? Can you tell me the next step? Which are the elements we need to be exchanged?
4 1.
Yes, that's correct. We have to exchange the root with the next location. The element placed at the next location. So we have to exchange 4 and 1. So actually this 7 is already added. So we can exchange this 4 and the element in the next location. So If that is the case, then 1 comes at the root, 1 will be at the root, and 4 will be at this location. Okay, 4 is already added. So we can use a. Do we need to rebuild the heap? Is it okay? Is it satisfies the heap property?
Rebuild ചെയ്യണം.
Yes. How?
3 exchange 1 and 3.
Yes. Again, we have to compare the root element and its children. Root element is less than the children. So we have to do one exchange, which is the maximum element. Maximum element is out of these two children. We are having 2 and 3 as children. 3 is maximum. So we are exchanging this 3 with the root. So we will get 3. 1, 2, 4, 7. So 4 and 7 are already over. So we can represent it as an array. So we will get 3, 1, 2, 4, 7. 4 and 7 are over. You can put a circle. Okay. Now the heap is okay. What is the next step?
Array 3 and 2.
3 and
2.
2. 3 and 2.
അല്ല ഒന്നുമില്ല.
Exchange 3 and 2. Exchange 3 and 2 because 3 is at the root element. So exchange these two elements 3 and 2. After exchanging 3 and 2, you will get like this. You will get element like 2 is at the root and 3 is at this location. So is it okay? Root must be greater than its children. But we had already, this 3 is the maximum element. So no need to consider 3. Then this heap is okay because the children of 2 is actually 2 has only one child, 1. So it maintain the heap property. 2 is the parent of 1 and 2 is larger than this one. So it maintain the heap property. So we can continue. So the array becomes like this 1, 2. Sorry, in the root it becomes 2. So array will be like this. You will get 2, 1, 3, 4, 7. We had already processed this 4, 7 and 3. Now we have only 2 elements. 2 and 1. What is the next step? Can you tell me the next step? Can you tell me the next step?
2 1 exchange 1 root
Yes. Exchange 2 and 1. That's correct. Yes. Exchange 2 and 1. You have to exchange this 2 and 1. Then at the root it becomes 1, 2, 3, 4, 7. Actually, we had processed these elements. 7 is over, 4 is over, 3 is over, 2 is over. Only 1 remains. So we can stop it here. So our sorting order is 1. Sorted elements are 1, 2, 3, 4, 7. That's all. Hope you got the logic. I will. Okay, let the numbers are 7, 4, 3 and 3, 1, 2. So first of all, we have to form a heap from these numbers. So numbers are 7, 4, 3, 1, 2. So 7 is at the root. Then we will fill the 4, 3, 1, 2. So now 7 is at the root. Which is the largest element in this series? Tell me which is the
7.
7. So 7 is at the root. Always the largest element will be at the root. So we have to exchange this 7 and the last element. Last element is actually 2. Look at this array. The last element is 2. So we have to exchange this 7 and 2. So after exchanging, we will get a diagram like this. So you can don't put this link because actually this 7 is not a part of this heap now. So 7 is at the sorted position. Okay, after exchanging this 7 and 2, we have to check whether the other elements are in heap order. So check at this. At the root there is 2. Children of 2 are 4 and 3. Is it satisfies heap property?
No.
No. What we have to do?
Exchange 4 and 2.
Exchange 4 and 2. Among the children, children are 4 and 3. Among the children, which is the largest one? 4 is largest. So we have to exchange 4 and 2. So 4 and 2 are exchanged. Then 4 will be at the root. So again 2 is at this position. Now 2 will be moved to this position. And 4 is at this position. Okay. Then again we have to check whether this area, this subtree. Actually 2 is greater than this 1. So this satisfies heap property. So what is the status now? Again the maximum element, second largest element is at the root. Second largest element is at the root means we have to exchange this 4 and the next second largest second position. Second last position. So we have to exchange this 4 and 1. This position. So 4 and 1 are exchanged. So 4 and 1 are exchanged means 1 will be at the root. 1 will be at the root. So you can delete this link. 1 will be at this position. So is it satisfies heap property? So 4 will be at this position. Is it satisfies heap property? Hello. Is it satisfies heap property?
No.
No. So we have to exchange among the children 2 and 3. 3 is the largest one. So we can exchange it. So 3 will be at the root position. So 3 will be at this position. So it satisfies heap property. So we can stop it here and we can exchange 3 with the next position. Actually 3 is at the third position. So what is the array status now? In the first position we will be having 3. Then 2, then 1, then 4, 7. So don't change this position, these numbers. So we have to exchange this 3 and 1. Sorry, before that we had exchanged this 3 and 1. So 3 will be at this position and 1 will be at this position. 1 will be at this position. So we can again, it doesn't satisfies the heap property. So these numbers are in sorted order. These numbers are in sorted order. So again we have to exchange this 2 and 3 because now 2 is at the root. So we have to exchange 2 and 1. So 2 will be at this position and 1 will be at this position. Again we can exchange it with the next position. So again 2 will be moved at this position. So the elements are in sorted order 1, 2, 3, 4, 7. Okay, let's explain the. So finally you will get a picture like this. Okay, then about So parent node means we have to return. So this is very important. Parent of I means it will be at the position I by 2. Left of I means we have to return 2 into ith position. Right of I means we have to return 2 into I plus 1. So algorithm, first of all, we have to build a heap. After building the heap, we have to exchange the first element with the last element. So first element from length of A. Length of A means total elements present in the list. That is N. N is the total elements. So 2 means we have to perform this exchange
Miss,
up. Yes.
slide. Uh,
Okay. So first of all, we build a heap from the numbers. Build a heap. Then after that, we have to exchange the first number a of I and a of I. I means here I is length. Initial value of this I is n. N means length of a. That is total number present in the series. Okay. So exchange the first element and last element. After that, we have to form the reheap. We have to reheap it, readjust it. So heap size of A is heap size of A minus 1 because one element is deleted from the heap. We had moved the largest element to the last position. That is why the heap size is reduced. So again, we have to call this function heapify A1. Heapify A1 is to adjust the elements in the heap. So this is the algorithm for build heap. Build heap means we have to, first of all, this step. First, there is one build heap is there. So first you have to build a heap from the series of numbers. So first, length of A is the heap size. So total elements present in the array is the size of the heap. Then we have to find the from length of A by 2 to down to 1. So length of A by 2 means total elements divided by 2. Down to 1, we can call heapify. Heapify means we are adjusting it. So we are calling heapify. This is the algorithm for heapify. It is very simple one. So for this algorithm, we are selecting the L. L means left of I. Can you view the slides? Heapify algorithm. Is it okay? L. L means it will return left of the current element. Left child of the current element is stored in L. And the right child of the current element is stored in the variable R. So left child is stored in L and right child is stored in R. Then first of all, we have to check the heap size. So L means this length, this cell, left child. So left child is less than heap size. If this L is less than heap size,
Miss,
yes. Okay. So this L means A means the total array. The full array is passed to this function. I means current element. So this L means index of the left child and this R means index of the right child of the current element. So this L is less than or equal to heap size of A. So total length is, if L is less than heap size means we can proceed. If length is greater means we cannot proceed. Actually, heapify function is over. That's the meaning of that. So next we have to check the left child is A of L means left child. This L means index and A of L means left child. If this left child is greater than current element, if left child is greater, then we have to we have to mark this L as largest. If this is not the case, then I will be largest. If this condition is false, then I will be largest. So if left child is largest, then we have to set this as largest, this L as largest. Similarly, we have to check the R right child. Here we had checked left child less than or equal to heap size. Here we have to check R less than or equal to heap size. Then we have to check this R is the index of right child. So R must be less than heap size. If R is greater than heap size, then the heapify function is over. So we can exit from this if loop. So, and the condition is right child is greater than A of largest. Right child greater means we have to set the index of right child as largest. So if A of R is, that means this right child is greater than A of largest. We had already set the, if L is largest, then we had set L as largest. If L is not largest, we had set the current element is largest. So whatever it be the case, we will be having one largest element. So now let's consider one example. Suppose our tree contains some elements like 7. 7 has left child as 4 and right child as 5. So 7, a current element is 7. It has a left child 4, right child as 5. So in the first case, we had checked L is less than heap size and A of L greater than A of I. Our current element is 7 and left child is 4. Which element is largest? Tell me, which element is largest? Hello. We
7.
have current element is 7 and its left child is 4 and right child is 5. Which is largest? Current element or left child?
Current element.
Current element is largest. So largest will be set as 7. Largest means it is set as I. That means we will set as 7. So then in the next step, we will be checking whether this 7 A of R. A of R means right child. A of R means right child. Which is the right child? Right child means 5. 5 is greater than A of largest. A of largest means 7. 5 greater than 7. Is it correct?
Correct.
Correct. So we can set the 5. Sorry, is it correct? 5 greater than 7? No, it's not correct. So we cannot set largest as the right child. Did you got the point? Okay, after that, we will check whether this largest not equal to I. Largest not equal to I means we will exchange the A of I and largest. So that means we had set in these two steps, we had set one largest element. If the largest element is not equal to I means largest element is not equal to the current element means we have to exchange either the left child or right child. Then we can call again heapify with the largest element. Okay, did you got the point? I will explain with an example. So convert the following array to a heap. So these are the numbers 16, 4, 7, 1, 2, 9. So first root element is 16. Then we will put it right left 4 as left child and 7 as right child. Then the left child of 7 is 1. Sorry, left child of 4 is 1 and right child of 4 is 12. Then what about the left child of 7? It is 19. So heap will be like this. After that, we will swap. We have to adjust this one. Is it in heap order? Is it in heap order?
അല്ല.
Allah. So we have to check whether this tree is in heap order. So first of all, we will check this one from this. We have to check this step, this 9 and 17. From the leaf node, we have to move up to the root. Okay, 9 and 17. Is it in order? So the last position is 19. Is it okay? Last position is 19. So we have to start from the 19. 19 and its parent. 19, which is the parent of 19?
7.
7. So we have to check whether that elements are in order. Is it in order?
അല്ല, ഓർഡറിലല്ല.
So, okay, so we have to swap 19 and 17. So it is in the next tree. Here we had swapped 9 and 17. And then we have to move to the next subtree, this subtree. Left subtree. 12, 4, 1 and 4. Is it in order? Sorry, actually it is in this tree. So here we have 4, 1, 12. Is it in order?
അല്ല, ഓർഡറിലല്ല.
So we have to swap 12 and 4. So we will get this tree. Again, we have to consider 19, 12, 16. Sorry, here, this step, this tree. 16, 12, 19. Okay. So again, it is not in order. So we have to move 16 and 19. So finally, we will get the tree like this. Biggest element will be at the root. We have to move that biggest element to the last position. That means we have to exchange this 19. 19 is at the root. We have to take this 19 out and move it to the last position of the root. So it will be at 7 and 19 are exchanged. So this is the case. So 19 will be in sorted order. So again, so we had moved 7 to the root. 7 to the root again. Is it in heap order?
അല്ല. അല്ല.
No. We have to call heapify. So not in heap order means we have to adjust it. First we have to consider the last position. Like that we have to adjust it. So here 7 and 16. 16 is the children of 7 are 12 and 16, which is the largest one, 16. So we have to swap 16 and 7. So 7, 12, 16, 1, 4 is the element. So after exchanging, we will get like this. 7 and 16 are exchanged. So we will get an array 16, 12, 7, 4, 1, 4. And sorted element will be 9. Again, what is the case now? 16 is the second largest element. Now it is at the root. So we can exchange this 16 and the next second last element. Which is the second last element? Last position. Element in the last position. Which is the element in the last position? Tell me. Which are the elements to be exchanged? We have to exchange 16 and 4. Again, 16 is the second largest element. It is at the root. So we have to exchange. We have to move 16 out of the root. And we have to exchange with 4. So in the sorted list, we can move this 16. Before 19, we have moved 16. In the sorted list, in this list, we have 116. After